hopefully that's close enough. All right, so questions on what the problem is asking? Thomas?
So it basically come down as 112 kilogram mass?
Right.
Okay.
All right.
Masses have no initial velocity.
Ah, thank you. Yeah, let's start it out with V. Its initial speed is 0 meters per second. Let's assume Earth. All right, we're dealing with energy here. So this, any other questions actually before we get into solving? All right, so while it is moving, what are all the forces that are possibly acting on this thing?
Gravity. Force. We've got a normal force.
Friction.
Oh. We'll make it frictionless. We'll wait for the test to have friction.
Yay.
Of course.
All right, so the first force you said, I'm going to nitpick.
Gravity.
Nitpick.
Gravitational.
Gravitational. Sweet.
Okay. Gravitational force.
Gravitational force.
Or weight. Also weight. All right, so gravitational force, what else?
The normal force.
All right, and there's going to be one more force involved.
Spring force at the bottom, right?
It'll be a spring force,
Yeah.
not static.
More than
All right.
Oh, but that's not the problem.
It will eventually hit the spring, which is a very faded green right here.
Does it matter how long the spring is?
Not in my drawing, no. Assume the spring is long enough that it will be able to compress however far it needs to.
Oh.
It's a perfect.
Yeah, they're not going to, to date, I've never done a spring that will hit the spring and just, it'll completely interfere with itself. If the spring interferes with itself, you know, like a slinky is right now, it's interfering with itself, it's not falling. That's no longer ideal. So we're dealing with ideal right now.
What if it's out, like a coil, like on a car or a truck? Or
So if it's out like that, it's gonna hit it. I'm not dealing with a point where it's gonna
and
basically,
it bounce back out.
yeah, it will compress or stretch however far it needs to. All right, so it's hitting the spring. All right, so the three forces, sorry, back to it. Of the three forces, which ones are conservative?
Gravitational force.
That's one. Any
And
others?
Spring force as well, isn't it?
Yes, it is. So the elastic force of an ideal spring is also conservative. What about normal force?
Non-conservative.
But why do I not care about the normal force in this problem?
Because it's perpendicular. It's always perpendicular to the direction of motion
In this problem?
in this problem.
Yes. It is possible to have normal force not perpendicular to the direction of motion. An example is there, right there. So, but in this problem it is, and if the normal force is perpendicular to the direction of motion, what does that mean?
Well, the dot product is a zero.
Yeah.
All right, so I heard two things at once and I missed most of both. So Justina?
Would be equal to gravitational force?
No, not. It is once it gets down to the level part, but that's not the issue here. Thomas?
The dot product is always zero when
Yeah.
they're perpendicular.
And what does the dot product have to do with this? Why do we care about the dot product? Besides just natural caring about things.
That's a good question.
Wait, we can ignore the, no.
Because the work is equal to the integral of something dotted with the
Force
direction of
times
motion.
Force dot distance, right? No.
Displacement. All right, so
Yeah, no.
the full definition of work is force dot dx, dr, ds, whatever letter you're using. So the key thing is the dot product there, because any infinitesimally small change in motion is always going to be along the path, and it's always perpendicular to the normal force. And so from this, the work from the normal force is equal to 0 joules. So hopefully this will remind you back to when we were doing this before. We are dealing with work and energy. What are the three work energy relationships?
We have, no.
Work total is equal to change in kinetic. Work non-conservative is equal to the change in energy. And then the work conservative is equal to the negative change in potential.
All right, so we have our three work energy relationships here. The first one being called the work energy theorem. The fact that there's no non-conservative work means that the energy does not change. E initial equals E final. And those are supposed to be capital E's. We assume this thing is not spontaneously combusting on its way down the path. Therefore, what are the two types of energy we care about here?
We care about
No.
potential energy and
Yeah, potential and kinetic. All right, so we have K initial plus U initial equals K final plus U final. All right, here we go. You're primed, you know it, in unison. It's gonna be beautiful. At the same speed. I'm hoping there's not gonna be a lag there. Here we go. What is the formula for kinetic energy?
1/2 mv squared.
It's got that wrong.
For those who are not here, this is the course papers. All right.
they said it at their house.
Yes, they just got this out.
What's the formula for potential energy?
It depends.
All right. So we have two different conservative forces involved, so we'll have two different potential energy formulas. Let's start out with what is the potential energy formula associated with the weight?
Mass time.
And what is the potential energy formula associated with the ideal spring or a plastic material?
1/2 kx squared.
I did not give myself enough room there. I put delta x here to indicate that we're dealing with a change from whatever its equilibrium position is. Some books will just write x with it's understood that x is from wherever the equilibrium position is. This is final and that is initial.
I'm a little confused. Wait, why do we care about kinetic right now?
As a matter of course, I mean, often in a problem like this, I would start out, in the more complex problem, I would actually have another mass down at the bottom and it would run into it. I would have started it as two separate ones, but we're not quite there yet.
Well, isn't all of the potential gonna go into the spring?
It will,
Okay.
it will. Also, I guess two things here. One, as a matter of habit, to always think about kinetic energy. Now, in fact, for this problem, for part A, we don't need it. Part B, we do need it. So it's a question of, we can leave it out now and then bring it in later, or put it in now and just ignore it to start with and then not ignore it later. Depends on your style. All right, so what is zero?
Initial velocity.
Let's nitpick that. The nitpick, I mean, what you said is absolutely right. However, we don't have to be that specific.
Initial kinetic energy.
Why is it equal to zero?
Because it's not moving.
Okay, therefore, what I'm getting towards is what does V stand for?
Velocity?
No,
Speeds?
Oh.
speed.
Isn't it?
Now, because velocity is zero, speed is also zero, but v here, I just want to emphasize that v here is speed, it is not velocity, there's no vector symbol involved. So that's zero because it says up there, vi equals zero. All right, what else is zero?
Well, if it's up there right now.
Final height.
Final height?
Yeah.
Why is that zero?
Because he said so.
That's in the spring.
Because Matt said so.
Also, the final kinetic energy, because final speed is zero.
The spring is not at its maximum compression if it's still moving.
The initial spring energy is zero because it's at equilibrium.
So what you're left with, mgh initial is equal to 1/2 k delta x final squared. We're trying to find this is implied maximum, this is at a maximum when these other two are zero, bless you, or especially when the kinetic energy is zero. So we're left with delta x equals the square root of 2mgh initial over k. Bless you. So that becomes the square root of 2 times 12 times 9.8 times 10, take the extent, divided by 30.
78.4.
Newton.
Yeah, meters.
So almost a football field.
That's a big spread.
And now the next piece. So now this 12 kilogram mass hits the spring compresses that much and is coming back. So when the masses separate, let's assume that they separate at maximum compression. Somehow there's some magic switch on there that says when the speed is zero for the second time, that there's some mechanical device that suddenly unlatches. So now they're both being pushed back. At what point will the 5 kilogram mass separate from the 7 kilogram mass? I mean, actually, physically, they have a distance between them.
When the spring is at its maximum stretch.
Before then?
It's from the point from when they stop. Like the point of maximum compression will be 78.4 meters, right? From the maximum compression.
That's not the point at which there's physically a distance between them.
Oh, wait, when did-
They'll stop or separate on their way back down the hill, won't they?
So
Why?
the 5 kilogram mass has, it's less mass than the 7 kilogram mass, so that force, when it pushes onto the 5 kilogram mass, is gonna accelerate it faster than the 7 kilogram masses go. So it's as soon as it starts to push back.
No, not as if, because I think that's what,
Wait, no?
no to is when as soon as it starts to push back. If they're still touching each other, they might separate, like physically there's no longer glue or whatever, some mechanism holding them together at maximum compression. But when it starts pushing back, they're still touching each other. So the question is, at what point will there physically be a separate distance between them?
The natural ones.
Once the spring reaches its natural state again.
Yes, not the maximum extension.
That's
the
kind of what I was
natural
trying to say
state.
with 78.4.
Oh,
So
because
from
it
the
was
distance it
transferred.
stopped,
Oh.
since it did 78.4 meters.
So the same distance as it is before it touches.
Yeah, they're right there.
Because it's so not kind
Because
of
that's as
stretches
soon as
more.
acceleration
Right.
is applied.
Okay.
Because it is as soon as it extends past that, the spring always wants to go back to equilibrium. So as soon as it gets past this point going this way, it now is applying a force backwards. And so the 7 kilogram mass is going that way, the spring is pulling back on it, so it will slow down. So that's the point, the 7 kilogram slows down, and 5 kilogram will will go at whatever speed that is back up the ramp.
But what he said kind of makes sense to me because force is equal to mass times acceleration. So if we
Right.
solve for acceleration, if they're experiencing the same force, then doesn't the 5 kilogram accelerate faster?
Because
They would actually not experience the exact same force if you broke it down that way.
Oh, okay.
Because you'd have the 7 here, the 5 here. This has the spring pushing on it, so this has force from the spring, and then there's a normal force this way and a normal force that way. And so what would be the same is that, so y is equal to 5a, and then fs minus y is equal to 7a.
So from the, it's like from the spring's perspective until it reaches this natural point, it's still pushing, it's still pushing. They're separated, but from its perspective, it doesn't have that.
Right, yeah, I mean, you can treat it as a single system or a separate system. I was trying to come up with a better analogy. Okay, this is a weak analogy, but I'm going for it anyway. For a spring hanging vertically, I have more force exerted on this coil than I do on this coil.
Oh, okay.
That,
okay, so what if the 7 kilogram mass was behind the 5 kilogram mass in the starting point?
then I would have the 5 kilograms stick to it, and the 7 kilogram would go. What would change here is the 5 and 7 would switch. You'd have a different normal force, the acceleration would still be the same.
So would they still separate after?
Yes.
It's still separated at the same point.
Okay.
Whatever the spring is attached to, as soon as it passes its equilibrium spot, it's gonna start pulling back.
Okay.
All right, other questions up to here? Do watch out for wording like this. When the 5 kilogram piece is 4 meters up the ramp, question is what is the direction of that 4 meters?
Is it along the hypotenuse or is it straight up?
It's along the hypotenuse. When I say up the ramp, that's up the ramp. That's not 4 meters above the ground. It's up the ramp. And I don't necessarily put that in language. I know in previous tests I used this language right here. It wasn't that, oh, I'm gonna trick them. It was just, that's the way my mind was working when I wrote it. And so that's the kind of thing that I do sometimes. So we're dealing 4 meters up the ramp here. Let's assume it's not. It somehow smoothly transitions from one to the other. It's 4 meters this way. I'm not giving you the equation of the actual curve right there, so that you have to do line integral, then we're not doing that. So this is 4 meters. So the question is, how far actually up does it go? And so that's just a little bit of trig. So that's 4, this is 60 degrees. So the actual change in height.
Isn't that 3, 4, 5? No, it's not. 2, 3, 4, 5?
It's a 30, 60, 90 triangle.
Yeah, that's not the thing.
4 times 60, which is 4 times 0.866. So 4, 2, 6, 3.4.
4, 6.
464.
Meters. All right, so this mass has now gone up. We now have these 2 different masses involved here. So we now have to be a little bit careful. Wait a second. Well, actually, okay. How fast is the 5 kilogram mass going at this point? Before it gets to the ramp, how fast is it going?
Oh, wouldn't it be, well, it's the same as the final velocity.
Which was
Which was zero.
zero.
Well, the
It's a
front,
Zen thing. There is no ox.
4.427 meters per second.
Is it 4.427?
Yes.
Well, let's figure it out. We know that it separates from the spring when the spring gets to its equilibrium position. So on this journey backwards, we know that all the energy, so the journey backwards, it initially is at zero, so this is when it's compressed. So this is at compression. This is the 1/2 times 30 times 78.4 squared. And that's equal to 1/2 times 12 times v squared plus 0 plus 0. The point in which the 5 kilogram mass reaches its maximum speed as it's being launched off is at equilibrium. That's when all the energy is back into kinetic at that one moment. And that's basically what you did?
Well, energy is conserved throughout this problem, like all the way up until
Yeah.
that point. So I just did square root of 2gh.
That would tell you the potential energy,
I said mgh equal to 1/2 mv squared. Since this isn't going to be, it's not going to go back to
Oh,
the same amount.
you're saying that's the speed at this point right here?
No.
That's the speed at this point right here. That's how fast they were going when they got down to,
I changed my answer to 14 meters per second.
anyone else get 14 meters per second? Recognize that this right here, this is the total potential energy when it's fully compressed. That is also equal to the total potential energy at the very beginning of the problem, which I assume that's what
That's
you did.
what I was doing.
That's
I just
what you
forgot to
did.
multiply by height.
Pesky height. So you could have done MGHI instead of 1/2 kx squared.
That's a wrong answer.
14 meters per second, a second to it, is he seconded?
my answers are right, so it's okay.
It is not carried.
Yeah, that's what I got.
Did you do square root?
I did. 0.5 times.
When I did it the other way, I got that as well.
So that would be 2.5 times 70, so it'd be,
But yeah, 1.2 doesn't make any sense. That's like
no, actually,
300 miles
because
an hour?
that's, was this 78.4 correct?
No.
Probably.
The 78.4 was not correct.
Oh, that could explain.
It's
some
supposed to
things.
be 8.85.
8.85?
Yeah.
Ah,
thinking, how long
I was like, that is.
break will have to
Just
be.
say, 123 meters per second is
too bad.
250,
Blind faith.
it's like 250 miles an hour. That thing is flying.
All right, does 14 now work?
Let's try.
13.99.
14. Raised you. 13.99. Really have to stop saying that. All right, so it's going 14 meters per second or 13.99, depends on where you are in your work.
Or 120.
If you're designing something for you engineers, designing something where lives are at stake, then yeah, you might want to take those couple extra decimal points. All right, so that's how fast it's going. So now the question is, when it gets to here, well, actually, we now know how much energy is, we know how fast it's going here. We can now figure out how much energy is in this. And whatever energy is in that, we take away from our total amount of energy, and that's what's left over in the 7 kilogram piece. So let's give ourselves some room. So we have some total amount of energy. mgh 1/2 k x squared, assuming that you have the proper x. So if we did our total amount of energy, we can start with what we start with initially. So that would be 12 times 9.8 times 10. What is our total amount of energy?
1,176.
1,176
joules.
Yes. That is how much energy we have to play with. It gets converted all into elastic potential at the end of part A. In part B, this is taking some of the energy away from it, from the system we had over there. So our energy gets split between the 7 kilogram mass and the 5 kilogram mass. The amount of energy in the 7 kilogram mass in part B, so part B, the energy of the 5 kilogram, is 1/2 mv squared, which is 1/2 times 5 times 13.99 or 14 squared.
It is 14. It's square root of 196. 2 times 9.8 times 10.
Oh, so 13.99, you get that from 8.85?
8.85, yeah.
You've got to take
good.
all the decimal points from that.
Yeah, I think it is 14. The 8.85 has rounding involved. So this is 196 times 2.5. Roughly 200 times 2.5, which is about 500, but we're just shy of that.
490.
Okay. So how much energy is left over in our 7 kilogram mass?
Well, 1176 minus 490.
686.
Yep, 686 joules.
Since the 7 kilogram mass is attached to the spring, it's all in the elastic. And so this 686 is equal to 1/2 times kx squared, which is 30 times delta x squared. So that divided by 15.
$45.73.
45.73
And then it repeats forever.
is delta x squared.
Yes.
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 That's 6.89 or
76
76
meters. So that's how much further it goes out.
That's how far it is from equilibrium. We do not know from what we have right there whether it has been compressed that much or extended that much. That would require a little bit more information and dealing with timing.
Can you say again what is it 6.76? So it's going that way, 6.76?
So what we figured out that we started out with this amount of energy. When the 5 kilogram broke away, it took away this much from it, so this is what is left over for the 7. Since the 7 is attached to the spring, it's in the elastic, so all this is telling us is that the 7 kilogram mass is 6.76 meters from the equilibrium position. We do not know whether it's closer to the wall or closer to the slope. We just know it's that far away.
Okay.
So it says when it's 4 meters up the ramp. Did we find it when it was 4 meters up the ramp?
No, as I started it, I realized that we didn't have to.
Oh, so it's
Because all we really cared about was how much energy was left over in the 7 kilogram.
Okay. Because the total energy is good, when it separates, is gonna be the same. It's just gonna be split between kinetic and potential.
Misinformation.
Let's say,
Yes. Yeah, so the 5 kilogram will have the 490,
Okay.
all kinetic, and then slowly turns into potential.
can't you just find,
Okay.
I'm sorry.
you know,
Once we see the equilibrium positions, what we're supposed to think of once we see that, like when I see, the velocity, okay, like when I see that thing, that thing is constant velocity, it's directly come up with acceleration is equal to 0. Once I see the equilibrium position, what I'm supposed to think of, like,
You said equilibrium equation.
position? Like
For-
here,
This,
For delta x equals 0.
for the most part, it's not in equilibrium. There's a small little stretch between the spring and here where masses are in equilibrium, but other than that, it's not an equilibrium problem.
okay, what does the equilibrium mean in the, in this case, like, I don't know how to
Are you
explain
talking
it,
about
I mean, what is
equilibrium position?
this right here?
but,
This-
like here, when I see that in the,
Oh, this equilibrium. Ah, okay. All right. A spring has a natural length that it'll just sort of, so if I hold the spring up like this, assuming it's not, ignore the small little oscillations there. That's its equilibrium position right there. So if I apply a mass to it, it'll stretch past that, and then it'll oscillate back and forth around that equilibrium position. So this just happens to be horizontal. Let's make it smaller so I can deal with it better. All right, so we have an equilibrium position here. As I stretch down, it's gonna oscillate back and forth around it. So when it's below the equilibrium position, the spring is going to try to pull things back up towards it. When it's above, it tries to push it down towards it.
okay,
So the equilibrium position is just when the spring is in its natural state. Delta x in this formula is how far it is away, it's the displacement from the equilibrium position
So,
of a spring.
so it's always gonna get that.
Yeah,
Well, in this
you could
case-
make it,
in these cases, it'll always be positive, or,
from a technical math point of view, yes, it's always a positive number.
well, considering all the delta x's are squared.
So we can.
Yes,
so our final H is 0 because that equilibrium,
our final position is,
I mean, final, H,
H final of mg.
H final is, we can make H is equal to 0 wherever we want. Matt spoke up first, at least he's the first person I heard.
okay,
And Matt said, let's make H is equal to 0 here.
Yeah, it's a very caution.
Did it make sense?
Dr. Fox just got his job taken.